So I think my screen is visible.
Yes.
Okay, right. So earlier we have discussed in the OSI model that we have around 6 layers according to the OSI model, and according to the TCP/IP model we have total of 5 layers. So if we go layer by layer, the first one is the physical layer, right? The second one is the data link layer, right? Okay. Then we have the network layer. Then we have our transport layer, and then application. So this is according to our TCP/IP model, and which actually we see in Wireshark packet captures as well. So that is what we use, right? So now from this we have discussed about this a few protocols we have discussed within the application layer. That's done. Transport layer we have discussed a little bit about, and then network layer we have discussed a little bit about. Now we'll discuss a little bit more about data link layer and the requirement of data link layer, and the major important thing what data link layer actually does, right? So the main job and role of data link layer is to get the MAC address of the devices to which we are sending the packets, or from whichever device we are trying to send the network packets, right? So what is a MAC? So what is MAC? It is nothing but it is media access control, right? And it is a physical address of the device to which we are sending the packets. By packets I mean the network packets, right? Not only to whichever device we are sending, whichever device is also receiving the packets. So sending or receiving, any device should have a MAC address, right? So now this particular MAC address, how is it known by the device who is sending the packet to the other device? So earlier we have discussed, and like I have drawn a router here, right? And then another router here. This router is connected to a desktop machine, and this router is connected to a desktop machine here. Okay, and this is the internet here in between, and this is the connection it is making with the other router, right? So through the internet there are multiple other routers. So in just for understanding, I'm creating one router at this portion and one router at this portion. The cloud here indicates internet. So this is how actually it is denoted when in future you will look at the diagrams. When you in future you will go to an infrastructure and you see the internal diagram of the network, you will see the diagram in this fashion, right? So a desktop PC will be here, and then a router, and then it is connected with a Ethernet cable like this to each other, and then through the cloud, which is the internet, right? So now the major importance of MAC address is to route the packets or to send the packets to the exact device, to whichever device we want to send the packets to. So earlier, I believe I have told you that IP address can be same for multiple devices, right? So if IP address is same, then how will you send the packet to the exact device? So that is going to create trouble. So for that purpose, and in order to avoid that kind of a confusion for the network packets to be sent to the destination, what we have done over here is we attach or we create a Ethernet header, that is our MAC header, right? So we attach these headers and we encapsulate the IP packet in between these headers. And after this, this packet is sent to the wire in the form of bits, right? So in the form of binary zeros, ones, one, zero, like that. So within your wire, it will be like this. But when it is in the layer two, that is when it is still within your router, in the layer 2 portion of your router, there it is going to attach this particular Ethernet header to the IP packet. So now, how does this particular device know the MAC address of this particular device here, or this particular device here? So in order to know that, what it does is there is a protocol in layer 2 which does this job of getting to know what is the MAC address of the destination, that is called as R. Right? R stands for Address Resolution Protocol. Right? So what does R do, and how does it resolve, or how does it get to know what is the MAC address of the destination to whichever we are trying to send the packets? So it is simple. So what happens is R is stored within your network devices. Let's say on your router, it is stored, and also on your device. TCP IP module or stack, right? So this ARP table, there is a ARP table which is created within your device TCP IP stack and also on your router, so that your router here, once the packet comes from here to here, your router checks that, okay, so the destination seems to be so and so IP. Let's assume that this device IP is 192.168.0.0.10, right? And this device IP is 192.168.0.1. So we have the IP address, we sent it here, and once it reaches this particular router, there are multiple other devices here, right? Let's assume that there is another device here with the same IP address as this 192.168.0.10. So the router is aware until now. Let's assume that there is no MAC address. Let's assume that router only knows IP address as of now. So it is seeing that there are two IP addresses. Now the job for router is difficult to send the packet and to whom it shall send the packet. So in that case, what this router does is it keeps doing this check from time to time. How it does is it sends a ARP request packet. Please make a note of this right away. So it sends a ARP request packet, right? And in ARP request packet, what it sends is it sends the IP address. It sends a ARP request towards the destination IP, right? And the destination IP in this case is it sends the ARP request to this particular IP address here, to 192.168.0.10, right? Once it sends the ARP packet here, and it sees there is a field which is left empty by the ARP request packet, and in that, if you see, it will be empty for MAC, and there will be a question mark, right? The destination is this. Now the source IP for the same ARP request packet will be the router's IP address. Let's assume the router IP address over here is 192.168.0.1. Okay, we used 0.1 here, so let's assume 0.2, right? So the source IP will be 192.168.0.2, and the destination will be 192.168.0.10. The MAC address is not known for the destination, but source MAC address we know. So let's assume the MAC address is f dot some 01 dot some MAC address is there. I'll tell you how we notate like the notation of the MAC address shortly. So this is the MAC address, right? So the moment this packet is reaching within the network to this particular destination, this destination sees that the MAC address is empty. So this means it sees that it's a ARP request packet. So what this device does is it replies to that ARP request packet by sending a ARP reply. And in ARP reply packet, the source becomes 192.168.10, and the MAC address becomes the MAC address of this particular device, right? And the destination becomes the router's destination IP, and the MAC address already this device is aware of that is this. So now what happened is the router opens up its ARP table and writes and maps it here, IP to MAC. And the device also opens up its ARP table and maps the IP to the MAC. So what it does, so the device here sees that I got a ARP request packet from 192.168.0.2, that is the router, and the MAC address is so and so. This device, after it receives the reply back from this particular device here, this router over here also makes a note of the same. It makes a note of 192.168.0.10 as the IP address of this device and the MAC address of this device. So now since this router is aware of the MAC address and the IP address, it's easy for the router, whenever this guy sends some packet over the internet to this router, this particular router is aware that, okay, great, now I have to send the packet here. Simple. So that is the job of ARP. Right? Now, once ARP is done, once we get to know the MAC address of the destination or to whichever device we are sending the packet, how does this particular packet is encapsulated? So earlier until now, what we have learned is there is application data, right? So this is the data over here, right? This is encapsulated within the layer 4 protocol, that is TCP or UDP. So let's assume TCP. And then this is again encapsulated within an IP packet, right? So the IP header is there. So this IP header is encapsulating the overall TCP and the data, whatever it is. So until here, we have learned for the layer 3 network layer. Now, what happens in the layer 2 is, since the layer 2's job is physical, so its job is to send the data within the physical hardware, not logically over the internet or in a software or within the computer system. So its job is to send it to the physical devices. So what it does, it adds Ethernet header to the start of the header here, to the start of the complete packet, and it adds the destination header to the end of the packet here. So both are Ethernet headers, destination header and the source header. Simple. So after this whole data is then sent via wire to the destination, and the destination then sees what is the destination header. If the destination header matches to whatever MAC address it has, it will start processing in the physical layer, that is on the router or on the switch, right? Once that is done, these two headers will be removed. Then it will check which IP address it has to send. Then it will remove this also. Then it will check which TCP port the data has to go. It will remove this header also. And then finally the user will be able to see the application data in a clear format after these all removals of the headers, once it reaches the destination. But before you send the packet, this is what the process is. The application data is encapsulated within the TCP header. The TCP header and the application data together is encapsulated within the IP header. This whole IP packet, the IP payload, is encapsulated within the Ethernet header, right? So until now, what we have learned about ARP, right? How it is getting to know about MAC addresses for the destination, right? And we have learned how this particular Ethernet header is responsible for sending the packets or receiving the packets. So done. Any doubts on these two? Any doubt on the ARP request and ARP reply? Because this is what is the process. Just how you have learned about DHCP, the flow, TLS, the flow, right? And for DNS, whatever is the flow. Similarly, there is a flow for each and every protocol. So for ARP, that is what the flow is. This is how it actually works. I'll show you a packet capture. A sample packet capture would obviously be available online. I'll show you that. In that, you will see the ARP packets and all. And I'll also show you how the device MAC address looks like. So let me just show you that. Just a minute. Okay. Right. So you can see over here that I have run a command for arp-a, which is showing me the complete ARP table which my device has stored within itself. So for each interface, whatever ARP protocol negotiations happened. So whatever negotiations regarding I just told you about ARP request and ARP reply, whatever negotiations have happened for that specific interface, it stores a separate table altogether. So you see, for this particular interface where the IP is 91.1, for that interface, it has got to know many IP addresses and their own physical addresses, right? So you can see over here, there are some class D IPs as well, 224, 224, 224, which are supposedly being used by the device for routing the packets internally. But you can also see for these all IPs, the MAC address or the physical address is varying, right? So this is how the MAC address is actually notated, like how it is annotated or how we actually write a MAC address. So I'll just take a copy of this as an example. And one more thing, if I show you here, I showed you yesterday the ipconfig output, and I told you that for each device there is a physical address. So let's see. Over here we see Ethernet Bluetooth adapter. So the Bluetooth adapter, whatever I have got on my device, it has a physical address as this. This is called a MAC address. Similarly, for my other adapters, if you see the Wi-Fi adapter, this is the MAC address. Right? Uh, where is the MAC address here? Yeah, physical address. So here VMware network adapter, we have this is the physical address. Right? Similarly, this is the physical address for this. Right? And now whatever ARP table, ARP-A physical addresses we see over here, these addresses are of my router, or they could be the physical address of my other devices. Let's say it could be my mobile phone, or it could be my smart TV at my home, right? Or it could be the other router to which I am connected to. So your device keeps this information handy with it because it keeps on receiving the R packets, right? So let me show you. Okay. So this process of ARP request and ARP reply in the layer 2 keeps happening. How does it happen? So let's say you powered on your device in the morning time, right? The moment you power it on, your TCP IP stack comes into picture, and the moment it connects to your Wi-Fi router, it sends those packets. So initially, when the device boots up, its initial thing what it checks is ARP, because this is the most important thing of the OSI model when you want to send a packet to the destination, right? So once this is done, the next thing is it checks for DHCP, right? And then it checks for the DNS. Then it checks for the all other things whatever are there on the sysstack. So this flow can be changed, but ARP is important and it starts first. Why does it start first? Because without the destination physical address, you cannot know who is the DHCP server, who is the DNS server. So within your network, when you turn on your laptop, your router is connected via Wi-Fi, or it can be connected via the LAN cable. It doesn't matter. What it does is it sends a ARP request packet to whichever device you are connected to, right? The moment this ARP request packet reaches here, this guy's responsibility is to share the ARP reply back. So once that ARP reply comes back, this device gets to know the MAC address of this particular device here. And similarly, so on and so forth. Let's say there are some 3 or 4 devices connected, right? So when these devices are connected like this, since these devices are connected to each other, this device knows the MAC address of this device, and this device knows the MAC address of this device, right? But there might be some scenarios when you send a broadcast message within the network. At that moment, when this device sends that sort of a message, that message reaches this device as well. And at that point of time, there is a ARP reply packet which goes to this device. So this device also gets to know the MAC address of this device, which is in the same network. Right? So once this is done, it's easier for these devices to communicate with each other whenever they want to communicate, because they know the physical address of these devices. So this device knows the physical address of the router, so it sends the packet here. The router is aware that this is the destination, so it sends it here. Simple. So that is how ARP actually works. Now, let's say, just a minute. So if we take a copy of the physical address, so how do we annotate ARP? Right? So ARP, whatever MAC address we have got, sorry, this is not ARP, this is MAC address. So the MAC address is 6 bytes long hexadecimal annotated unique ID of the device, right? So make a note of this, that MAC address is unique. So in the entire world, there are no 2 devices with the same MAC address until and unless you create one. Right? So for virtual machines, when we configure virtual machines, you can definitely create a same MAC address for 2 virtual machines. That's fine. But for in general sense, when you purchase a laptop or when you purchase a device, let's say you purchase the smartwatch or mobile phone, those all devices have a very unique MAC address. So how is this possible? Right? So how is this possible is, there is something called as OUI and vendor unique ID, right? So what is this OUI and vendor unique ID, right? So in this particular scenario, let's take an example here. So this is a 6 byte long MAC address what we have got, right? So 6 bytes is how much? Team, what is 6 bytes?
Forty-eight bits.
Right.
48.
So it's 48 bits long is the length of the MAC address, and it is 6 bytes, right? So the OUI and the vendor unique ID is nothing but the initial 3 bytes of the data is the OUI, and the last 3 bytes are the unique identifier put in by the vendor. So let us assume that you are a device manufacturing company. You have your own device manufacturing company. The moment you establish this company, you have to reach out to IEEE, right? Institute of Electrical and Electronics Engineering. So when you reach out to them, they are going to give you an OUI which is specific to your organization, right? So here if you see, this is 48 bits, among which if you see 3 bytes, 3 bytes is how much? 24 bits. So 2 to the power of 24. This many number of OUIs can be provided by the IEEE for now, right? So what this OUI does is, they will provide you the initial 3 bytes of the data, 3 bytes of a constant value, a constant hexadecimal value, which you have to input in each and every device, whatever you manufacture. No matter if it's a very small device also. If it has a network interface card and if it is going to act in the layer 2, simply they have to do this. So let's assume that you established a device manufacturing company, you reached out to them, they give you an OUI, let's say the OUI is 00. What happened? Uh, okay, I think my Microsoft OneNote started updating. Just give me a minute, it is updating. So any doubts, guys, until now? In the meantime, when it gets updated. Okay. Okay. So, uh, right. So yeah. So let's assume that you have been given by the IEEE for an organizational specific identifier, right? So whatever identifier they give, let's assume this is the three identifier which you also got 00, 50, and 56. So this is the hexadecimal value what they have given you for the OUI specific thing. Now, your job after when you manufacture each device, your job is to append this, and by append I mean you have to burn this on your device. Burn on the device, it means that whatever TCP/IP stack you are going to build and whatever physical devices you are going to configure, each and every device should have this particular MAC address when there is one specific NIC. For one specific NIC, that is the network interface card. For that you should have a specific MAC address. So this will stay constant for your organization, but whereas the other 3 bytes of information will be different according to you. So that you have to keep changing, right? And once these devices are out, finally for each device manufacturing company, for each device manufacturing company and for their each device, there will be no device having the same MAC address, and that is why a MAC address is called as a unique physical address. And this you can verify also. This you can verify. You just have to open your device, go to get MAC, or you can type the arp-a in order to get the arp table on your screen. The moment you do this in your command prompt, you will get all the IPs and the MAC addresses there. And for each IP, for each interface, you will have a different MAC. However, you might have the same OUI. As I told you that if the manufacturer is same, then you will have the OUI same, right? So that is about how the MAC address is actually configured within the factory, right? So now, if I show you how a MAC address actually looks like, so this is the MAC header, right? So this complete MAC header has few fields in them which actually is useful for the destination to understand what type of load it is carrying or what type of packets it is carrying within it. So accordingly, it will be processed by the destination, right? So we have a preamble header, we have an SFD header, we have destination source. This destination is not IP. This is MAC, the physical destination, right? The physical source, MAC, and the type, which is very important. So the type field actually keeps in itself the information of what sort of an IP packet you are carrying within it, because obviously it is a layer 2 protocol. So if it is a layer 2 protocol, it will be carrying a layer 3 protocol in it. There is no way it will be carrying directly a transport layer protocol within a layer 2 protocol. That's not possible. This flow will never be changed, right? So you can remember this. So if it's a layer 2 protocol we are talking about, definitely it should encapsulate the layer 3, layer 4 and layer 5. So directly this layer 2 will only be able to see layer 3. So accordingly, in order to inform the physical layer or the destination to see what packet this particular layer carries, the data link layer carries, the type field consists of the IP version what it is carrying. So it can be IP version 4 or it can be mentioned as IP version 6, right? And the data is nothing but the IP packet and whatever encapsulation it has. And what does pad means over here? So padding means nothing but unnecessary data in order to fill up this whole header of 48 bits, right? So let's say it added all the data and all, and then it didn't have that amount of data. Not 48 bits. Let the MTU is 1500 bytes, right? Let's say this 1500 bytes is not completed. It's still short of another 50 or 60 bytes. So that 50 or 60 bytes is nothing but your padded data. So you are adding that extra padding within this particular header itself so that this data can be transmitted, right? Now, at last, what we have over here is the FCS, the frame check sequence. So this frame check sequence is nothing but a mode of transferring the packets error free. So this doesn't mean that if this particular header fails or this particular packet, let's say it was carrying a packet of around 1500 bytes and suddenly it got some issue came in between, and then there are some packet loss or something, and the header has the FCS check has a value which is not matching to the value what it should be by the destination. So what happens is this packet is discarded within the layer 2 itself. Within the layer 2, that is the destination will see that FCS is failing. Let's discard this packet, and it will not send this response to the source to send the packet back. So that is now how FCS works. This is just to check if there are any errors in this particular packets. If there is an error and it is actually identified or being notated by the FCS header or the field in the MAC header, we will be discarding that packet simply. So as in TCP, we have learned that if any packet is not received or if any packet has some issues, it is retransmitted. So that sort of a mechanism is not there. That happens only in TCP. So TCP will look into it. So layer 2's job is to just discard that packet. The moment this packet is discarded, definitely the destination will know on the TCP layer that, okay, there is something which is lost. It can be multiple reasons. It can be the layer 2 dropping the packets, or it can be the network dropping the packets. Whatever it is, we will have to retransmit. So the TCP will check that, right? So I believe that you have understood. Any doubts? Okay. Now, so this is what is the basic information about the layer 2, right? Now, so I have told you that IP packets can be unicasted. What does unicast mean? One to one, right? Then it can be multicasted, that is one to many. Then it can be broadcasted, which is one to all. So you are just sending the packets to everyone. Now, when we see that IP is capable of this, we also have introduced you to the concept of ARP. So ARP also uses unicast, multicast, and broadcast in order to send the packets. So there are multiple scenarios. Let's say there is a new device within your network. Suddenly it came up. So it wants to advertise itself. It wants to advertise itself and wants itself to be known to the other devices within the network. It is connected to the router. The router is connected to hundreds of devices here, right? So what will this device do? It is not going to send packets to each and every person here, because until now it is not aware who is this guy, who is this guy, who is this guy, who is this guy. In order to understand these IP addresses and also their MAC addresses easily, what this device will do is it will send a ARP request packet destined to F F all Fs. So that is the broadcast address of the ARP packet. So the complete destination MAC will become as a FFFFF. So what will happen is this particular layer 2 packet will go here also, it will go here also, it will go here also, it will go here also, and it will go here also. And it will receive the reply accordingly. So now once it receives the reply, this guy will make an ARP table, and according to the reply it gets, it will write, okay, this IP address, this is the MAC address, this is the IP address, this is the MAC address, like that. So that is how I just showed you in the command prompt as well, how the ARP table was looking in my device. Right. Similarly, regarding unicast, it is simple. The moment this particular ARP table is ready, we know that this is the IP and this is the MAC address. So you will directly be sending the packets to this particular MAC address. So that is unicast. But for multicast, what happens is for each and every device, there is a separate multicast ID. So that we need not learn or need not understand. But there is a multicast feasibility for the MAC also is what we are supposed to be aware of. Right. So when we try to configure that multicast address, it takes a little bit of calculation and all, which is not at all necessary because we generally don't do ARP for multicasting. So that is not required. So the number one thing is you have to know unicast MAC addressing and broadcast MAC addressing. Right. So now I think we have covered a lot about ARP. I just wanted to cover something about security related to ARP. Right. So in ARP, what happens is, as I told you that there are ARP request and ARP reply packets due to which we are getting to know the MAC address of the devices within the network. But this ARP packet is not secure. Not at all. So you are just sending the ARP packet to random devices within your network. Let's say you are in a coffee shop, right? And you are connected to their Wi-Fi network. So that was free. You get connected to the Wi-Fi network, and this owner or some hacker on that particular Wi-Fi network has its own device which is acting as a which has a DHCP server which is acting as a malicious DHCP server, right? So this particular device here, whoever is the hacker, he has a DHCP server running. Now what happens? Generally, this particular router should send the IP address to this particular device. But since this particular device is advertising its own MAC address to everyone within the network, this guy knows that there is a new device which is having so and so IP address and so MAC address. Now what this guy will do is he has a very simple meaning here to do. What it does is it is going to assume itself as a DHCP provider and send the offer request packet to this particular machine. And this is the reason why I told you why you should know about DORA. So DHCP, you learned the flow, but in security perspective, this is how hackers actually create a back channel within your network. What they do, the moment they get the MAC address of your device, they are going to run a rootkit on their particular machine, which has a DHCP server, which has a DHCP potential on their own machine. So DHCP server does not require very big servers or something like that. It's a very small thing which you can literally install on your device and also do, right? So when this happens, what happens is this DHCP server will send a offer packet, because this guy will be sending a discover packet to everyone, because it wants to discover who are the DHCP providers to me, right? So what this guy will do, this guy will send the offer packet, and this guy doesn't know that, okay, this DHCP is malicious. So this machine will accept that offer and it will tell that, okay, I will reserve this particular IP and send the reserve packet back. And finally, this DHCP server will acknowledge it, and this guy who doesn't know that he is connected to a malicious person here will be accessing the internet via this device. So when this is going to happen, this guy, whoever is the hacker, will be running a software to intercept all your traffic. Let's say you are going to some sort of a bank website and you are making some transactions, right? So you just logged in there. The moment you log in, this hacker is aware of your user ID, your password, and your basic information, whatever you are trying to input there. These two are more than sufficient for a hacker to, uh, you know, encache or remove whatever is there within your account. They can do multiple things with user ID and password. However, these days we have the multi-factor authentication, but that also can be taken care of, right? So this is the importance of the security importance of ARP. That's the reason why people don't suggest you to connect to the free Wi-Fi networks in public places, right? So this is how ARP can also be utilized for hacking your own device, right? So that's the vulnerability of this particular vulnerability of ARP. Like that, there are multiple other vulnerabilities like ARP spoofing. So what does ARP spoofing mean? It is nothing but the hacker is sitting here, the router, whatever is the router is there, he is sitting here. This is the user machine over here. So what this ARP spoofing does is, this router has a MAC address, so and so MAC address is there. Let's say some MAC address is there. This particular hacker assumes this MAC address. So it hard codes or it creates a software where the MAC address is same as this router's MAC address. Now you see this particular device is acting as if this particular device becomes this router for this user. This user still doesn't know that he's connected to this guy, right? The packets are actually flowing via the router. That's okay. But the destination, because it is spoofed, it is reaching here also. And in that context, this particular hacker creates a back channel towards you and exploits your machine. So he or she, whoever is the hacker, can install rootkits on your machine, right? If you are going to facebook.com, They will take you to facebook.com, but the website will look like facebook.com, but it is not facebook.com. It is their own domain, and you are entering your user ID and password. You're entering your Aadhaar details. You're entering your credentials for the bank website. Everything is being noted down by them when this happens, right? So that's about ARP and a little bit about security features about ARP and MAC addressing. So we have covered ARP, we have covered MAC size, the notation, why is it important, the MAC spoofing, right? And now, any doubts you have on today's session? No doubts? Okay. Okay, so let me present my screen. I was running a packet capture on my machine and seems like my device is continuously sending our packets, right? So if you see this over here, I am running the packet captures and I have kept the filter as ARP. So I am filtering for the protocol ARP here, right? And you can see the ARP packets here clearly visible. So let me stream this. I think so I can stream it. Okay. Let's just show you an example. So if you see over here, the ARP is, I told you ARP is acting in layer 2, and that is what is happening here. We don't see other headers here. Remember in the previous sessions we have seen TCP, IP and all everything, but ARP is a layer 2 protocol, and that is the reason why this layer 2 is encapsulating this particular address resolution protocol, which is the request packet here, right? So we have any sort of reply? Yeah. So we have reply packets also, right? So let me show you. Now here, if you see, the hardware type it is showing as Ethernet because I'm connected via the Ethernet LAN, the cable, right? And then it shows the protocol type is IPv4. I told you type is very important. For each and every header, what we have got, the type is important. So you can see the Ethernet header is encapsulating the type as ARP. So it is telling that I am carrying address resolution protocol. And address resolution protocol is telling that I am carrying a IPv4, right? So now if you see here, the operation code over here is request is 1. So this operation code is requesting. So this request is going from whom? So the sender MAC address is this particular MAC address, and the sender IP address is 192.168.0.106. The target MAC address is 00000. This indicates to this 0.1 that this particular MAC address I don't know, your MAC address I don't know. So send me your MAC address. So now this 0.1 in my network is the Wi-Fi router which I am connected to. So let us see what response it has sent. So now it has sent the response as reply, and it tells me that the sender MAC address is router, and this is the MAC address it is. The sender IP address is this, that is the MAC address which I was actually requesting. And then we see the target MAC address and the target IP address. And if you see here, the destination over here is a broadcast destination. If you see the Ethernet header, where we see the source MAC address as this one and the broadcast as this one, because we want our device to check with everyone within the network who has this particular this particular IP's MAC address, right? So if your router is not responding, let us say your router is not responding, my router is not responding, but my broadcasted packet is reached by my other device, which could be my television or which could be my other laptop which is running, right? So that device can send me a response back also, because that is how ARP actually works. If this device, whatever device we are trying to look for, if this device doesn't have the information, since the packet is a broadcast packet which is to be sent to everyone, if that particular device knows who has the MAC address of this particular IP, then it is going to provide that, right? So in simple terminology, if you want to make a note of ARP's definition, it is nothing but you are resolving the IP address to the MAC address of that particular device. What is MAC address? It is a physical address of that particular device to whichever we are sending the packets, right? And if you see in the packets here, you see the destination is broadcast because we are broadcasting it, and the source is this. But the moment the reply comes back, we see it is unicast message. You can see this, the destination becomes my device and the source becomes the TP link, that is my Wi-Fi router, which I am connected to right now, right? So I think if I open my Mac table, I should be able to see that. Okay, so yeah, okay, I think you're unable to see the screen. Let me share it again. Screen two, yeah. Okay, so I believe you're able to see my command prompt screen and also the packet capture screen. Right. So I ran a arp-a command and I told you that your device keeps storing the information within the table interface wise. So according to the interface it stores. So currently, if you see the ARP packets here, I sent a request from which interface? It was from this particular IP address, right? So if I open my command prompt and see, the interface is this one, 106, which is matching this one. And it has a ARP table of itself inside it, right? So now this particular ARP table, if you see whatever reply we have received, yeah, we have received a reply. In this, if you see 0.1, we have the destination to whatever router information, and the physical address is this. So if you see the physical address, where is this? Yeah, this one here, E4 FA C4 97 9E91. It's matching the physical address. So this is how your device makes a note of the ARP table, the MAC table within its own TCP/IP stack, right? Once this job is done, so this data is staying like that only. And from time to time, whenever you're trying to turn off your system or when you're turning it on back, or from time to time, this particular process keeps on happening in the backend. So this doesn't disturb your network. It just is trying to keep and make a note of this particular ARP table. Simple. So for each interface, this is how it is going to do. And I was telling you about OUI, right? So if you see over here, there are some multicast destinations, internet IP addresses, to which there are similar OUIs, but the vendor specific portion of the MAC address is different. You see this? So this is what I was telling. So this OUI will remain same for the same vendor, right? And this will keep on changing. So within my network, I have two TP-Link Wi-Fi's at my home, right? But unfortunately, I cannot see the other Wi-Fi because that is in a separate network altogether. That's the reason why these R packets are not reaching that. But this is the same OUI what I have got for that other router as well, because that's also TP-Link manufactured device, right? So very important concept this. The moment interview questions start, they start from ARP, because you go to a browser, you open up a browser page or something. Before that, you need to know who is the destination, who is the source. What's the physical address of your internal network devices? That's the number one and major important thing. And for that, you must understand MAC and ARP. And after that comes our IP routing, VLANs, and all everything, right? So I hope you have understood, and we have also seen the things in a live scenario also within the packet capture. I should be seeing some other things as well, but I think my device is only connected here. There is nothing else here. Yeah, there are no ARP requests for other packets because it's not getting any information because I am the only one connected here in this network, right? So if you see this, I hope everybody is checking this on their own Wireshark every day after the class because you can see the ARP header as well here, how it is actually distributed. And I told you just now the Ethernet header, whatever is carrying this ARP header inside of it, when this Ethernet header is attached, you can see there is a padding section over here, right? And for this particular frame, it is adding a 18 bytes of padding, right? It is adding that padding in order to fill this particular minimum padding length, minimum Ethernet length. Because if you see the Ethernet address resolution protocol is 28 bytes, right? This is having overall of 32 bytes inclusive of this particular Ethernet header. In order to fill that gap, in order to make it a minimum of 46 bytes, it is adding this padding, right? And this is the type which is having all hashed values over here. It's showing what kind of information you're carrying, that is ARP obviously. And then later source and destinations are the MAC address. That's it, right? So that's it for today, guys. I think we'll cover further things tomorrow. I hope you have got to know what the layer 2 protocol and the significance of layer 2 is.